Okay, so let's get started today with our pre-lab run-through or lab run-through of the copper cycle experiment. The goal of this experiment is really to provide a survey of chemical reactions, all of which are involving our wonderful element of copper. So to break down the steps of this experiment, first and foremost, we're going to be looking at the oxidation of copper with nitric acid. So we have copper solid plus nitric acid So copper solid plus nitric acid, in this case, 2 molecules of nitric acid, leading to copper 2 plus, aqueous, nitrogen dioxide, 2 molecules of nitrogen dioxide, which is a gas, and 2 molecules of water, which is a liquid. So just counting oxidation numbers for a moment, we have copper 0. Hydrogen has a +1 oxidation number. For each of our oxygens, they have a -2 oxidation number. So the nitrogen in nitric acid has a +5 oxidation number. Copper 2 plus has a +2 oxidation number. In nitrogen dioxide, the oxygens have a -2 oxidation number. So the nitrogen has a +4 oxidation number. In water, hydrogen is +1 and oxygen is -2. Just checking that this equation is balanced here. One moment. So our hydrogens are unbalanced. So let's adjust our coefficients. And then in addition to nitrogen dioxide, we also generate 2 molecules of nitrate ion, aqueous. Now, if we continue looking at our oxidation numbers, so in nitrate, the nitrogen oxidation number is +5, the oxygen oxidation numbers are -2. Now, looking at this equation, we can identify next our oxidation half reaction is copper solid, leading to copper 2 plus, aqueous plus 2 electrons. Because we went from 0 to +2, we lost 2 electrons. Now let's look at our reduction half reaction. So for our reduction half reaction, we have nitric acid, HNO3, 2 molecules of nitric acid, leading to 2 molecules of nitrogen dioxide, plus 2H plus, just to balance out our atoms. Now, taking a look at our oxidation numbers, here, we went from a nitrogen oxidation number of +5 to a nitrogen oxidation number of +4. So because our oxidation number has decreased by 1, we have in turn gained a total of 2 electrons, 1 for each molecule of nitric acid. Looking at this half reaction a little bit further, we have 6 oxygens on the left-hand side, and we have 4 oxygens on the right. So in order to balance oxygen, before we start messing around with the H+, we're going to need to add a total of 2 water molecules to the right-hand side. So now we have an additional 2 oxygens. And now looking at our hydrogens, we have 2 hydrogens on the left, 4 hydrogens on the right. So we add 2H plus to the left-hand side. So this is our complete reduction half reaction. And this is a very common reduction half reaction you'll see for the reduction of nitrate. Okay, so here's our first step. If we wanted to break down this original equation into its net ionic equation, one fast way to generate a quick net ionic equation for a redox reaction is to simply add up your 2 half reactions. And so if we look at our net ionic equation, we have copper solid. And then let's now focus on, well, first let's write out our combined chemical equation and verify that this equation does in fact match up with the overall equation that we've established. So first and foremost, we have copper solid plus 2H plus 2HNO3 leads to copper 2 plus 2NO2 plus 2H2O. Okay, so far so good. What we're next going to do is we're going to dissociate each of our strong electrolytes. So this turns into copper solid plus 4H plus aqueous plus 2NO3 minus leads to copper 2 plus 2NO2 plus 2H2O. And here we start to see the true nature and the true oxidizing agent in this case, which is our nitrate ion. Okay, beyond that, there's nothing else that we can really cancel in this expression. So here we have our net ionic equation. For our first oxidation of copper. Okay, perfect. So after our first reaction in our test tube, we have a solution which has copper 2 plus ions and some nitrate spectators, which is, we can view this as a solution of copper nitrate in nitric acid. Now, in order to precipitate out our copper, the next reaction in this sequence is precipitation of copper 2 plus as copper hydroxide. So a common way of separating metal ions from solution is to generate a hydroxide. So OH minus or hydroxide salts are generally insoluble. And as a result, these hydroxide salts will precipitate out as a solid. So to show the full equation for this reaction, so if we have copper nitrate, aqueous, and we add 2 equivalents of a hydroxide salt or 2 equivalents of hydroxide in solution, will in turn generate copper hydroxide solid. So this is our precipitate, plus 2 equivalents of nitrate ion. If we want to look at our net ionic equation here, we can dissociate our copper nitrate to copper 2 plus aqueous plus 2 equivalents of nitrate anion. We do not dissociate our copper hydroxide because it's an insoluble species. We only dissociate our strong electrolytes and soluble ionic salts when writing a net ionic equation. What we see is that we have a spectator ion. This nitrate is just a spectator ion along for the ride. So our net ionic equation for this process is we have copper 2 plus aqueous plus 2 OH minus 2 hydroxide ions, leading to copper hydroxide solid. This is a textbook net ionic equation for a precipitation reaction. So we call this reaction a precipitation reaction. Which is defined as an exchange reaction that generates an insoluble solid. And we call this insoluble solid, such as copper hydroxide, a precipitate. If I was being fully correct, I would call this copper 2 hydroxide, following our nomenclature conventions. Now from here, in our test tube, now that we have our insoluble, so we have our solution, and at the bottom of our test tube, we'd have our insoluble copper hydroxide. So then, from this, all we have to do is decant or remove. So decant our liquid. And after decanting our liquid, we are left with a test tube containing primarily copper hydroxide. Okay, now from here, we can further process this solid sample to generate a metal oxide. So the next reaction we're going to look at is decomposition of copper to hydroxide to copper to oxide. Now, it's commonly known that if you take a metal hydroxide and subject a metal hydroxide to heat, you will generate a metal oxide plus water. This is a classic decomposition reaction. And this is a classic framework for the decomposition of a metal oxide. So by analogy, looking at our copper hydroxide, if we expose our copper hydroxide to heat, we can drive off the water and generate, in turn, copper 2 oxide and water, which is quickly removed and will evaporate off upon heating. So then, if we take our test tube containing our copper hydroxide and we expose it to a flame, a light Bunsen burner flame, expose it to some heat, we will quickly generate a characteristic dark solid of copper oxide, with our water just escaping out of our test tube. So this is a classic decomposition of a metal hydroxide. Now from here, what we're going to do is we're going to now dissolve our copper oxide. And to do that, we're going to proceed with an acid-base reaction. Between a metal oxide and acid. Now, depending on how you view the dissolving process, you can view this as an acid-base, you can view this as an acid-base reaction or an exchange reaction. So let's talk a little bit about this. So in this case, we're taking our copper oxide solid and we're reacting with a strong acid, aqueous sulfuric acid. That in turn generates copper sulfate, which is a soluble salt and has a distinct blue color. So let me use my dark blue highlighter and just go over copper sulfate. It has a very distinct dark blue color. And additionally, we also generate some water in this process. Now, if we look at the net ionic equation here, and if we think a little bit about what's going on the moment we add a little bit of, what's going on in solution, we see our copper oxide is an insoluble salt, so we don't dissociate it. Sulfuric acid is a strong acid, so it dissociates into 2 equivalents of H plus and 1 equivalent of sulfate anion. Okay? Copper sulfate, soluble salt, so it dissociates into copper 2 plus aqueous, sulfate ion in solution, and water, as it is a molecular compound, does not dissociate in net ionic equations. As we can clearly see, sulfate is a spectator present on both sides of our chemical equation, so we can simplify this process to copper oxide solid plus 2H plus aqueous leads to copper 2 plus aqueous plus H2O. So metal oxides are often considered quote unquote basic because when placed in solution, they generate metal hydroxides, which can react with acid, or metal oxides can directly react with acid, as observed in this case. So the reason why we call this an acid-base reaction is this oxygen in our copper oxide is serving as an H plus acceptor, which is a classic base. And we clearly have an acid. We have H plus or hydronium floating around in solution. So we have an acid. So we are donating protons to our base, ergo acid-base reaction. Now, just to be 100% clear here, in terms of oxidation numbers, we're going from copper plus 2 to copper plus 2. So there's no change in oxidation number. This is not a redox process. This is purely acid-base chemistry at play. But this leads us to our final reaction where we complete this redox cycle, where we regenerate copper solid, copper 0, by reduction of copper 2 plus with magnesium solid. So just as a refresher, if you look at your activity series, there are a few really critical points that you need to pay attention to in our activity series. So we have magnesium going to magnesium 2 plus 2 electrons. We have H2 going to 2H plus 2 electrons. And then below that, we have copper going to copper 2 plus 2 electrons. Now, as a refresher, if you can draw an arrow from the left-hand side, from your metal, your reducing agent, to your cationic species or your oxidizing agent, if your arrow is pointing down, so if your arrow is pointing down, that implies that a reaction is possible. As a corollary to this, if your arrow going from your reducing agent to your oxidizing agent on your activity series is pointing up, then the reaction is disfavored. Okay, so there are a few things that I'd like you to take away from this. First, if we draw an arrow going from magnesium to copper 2 plus, that reaction can definitely occur. Same if we draw an arrow from magnesium to 2H plus. So magnesium reacts with H plus and copper 2 plus. Okay, perfect. So magnesium can reduce both of these species in solution. Additionally, copper has this really wonderful property, that's why it's used in pipes a lot, and that it's somewhat acid resistant. So if we draw an arrow going from copper to H plus, we see that copper does not substantially reduce H+. And we can utilize this unique reactivity and this unique reactivity preference of copper in order to separate out copper from this acidic solution. So we're going to take our copper sulfate solution and we're going to react it with magnesium metal. Now, of course, all of these reactions are run in an acidic sulfuric acid solution. We still have sulfuric acid left over from our earlier steps. So the first reaction that we have is a classic displacement reaction, where magnesium is going to displace copper from this compound copper sulfate. So we have our pure element magnesium displacing copper from this compound to generate a pure element copper and a new compound of magnesium sulfate, aqueous. Now, if we look at the net ionic equation, just breaking each of our soluble species down further, we know that copper sulfate is soluble. We've established that previously. Magnesium solid, we can't dissociate pure solids and liquids further. So we have copper solid, and then magnesium sulfate we dissociate into magnesium 2+ aqueous and SO4 2-, our sulfate ion in solution. Again, we see sulfate as a spectator ion, and in turn we have a net ionic equation, of copper 2+ aqueous plus magnesium solid leads to copper solid plus magnesium 2+ aqueous. And as we can see, if we just look at our oxidation numbers, copper is going from +2 to 0, magnesium is going from 0 to +2. So if we had to write down our half reactions, our oxidation half reaction is magnesium solid going to magnesium 2+ aqueous plus 2 electrons. And this is the reason why I really like activity series, is we can actually figure out our half reactions just by staring at our activity series table. It has most of the half reactions there for you to transcribe. Okay, in terms of our reduction half reaction, we have copper 2+, copper 2+ aqueous, gaining 2 electrons to generate copper solid. If we add these two reactions together, we notice that electrons are conserved, and we have a complete redox reaction. Okay, so we've taken copper through this series of reactions, and in turn, we have regenerated our solid copper. So then, by comparing the mass of copper that you start out with, so it should be approximately 0.02 grams. And if we look at the mass of copper recovered, which will be less than 0.02 grams by definition, reactions are not perfectly quantitative and material can often be lost during purification steps. We can calculate our percent recovery in this case by taking the mass of copper recovered over the mass of copper that you start out with times 100%. So as you watch the video, I want you just to keep in mind that as you go through each of the reactions that we've outlined, I'd want you to focus intently on observing any color changes, trying to explain these color changes, and observing any potential side reactions that could be occurring and helping explain these side reactions. So just to help everyone along on this idea of side reactions, and side processes. So when we attempt to isolate copper, so we have our copper 2+ aqueous, we're attempting to reduce our copper 2+ with magnesium to generate copper solid and magnesium 2+. Remember I had this big asterisk saying that we have some sulfuric acid in solution? Well, this is a little bit important, and this is a hint for one of your lab questions. If we look at our activity series, we can see quite clearly that magnesium reacts with H+, right? So then, just as magnesium is reacting with copper, we also have our acidic solution reacting with our solid magnesium to generate magnesium 2+ aqueous and H2 gas and hydrogen gas. So you do want to be careful about lighting a flame near this second reaction to avoid accidentally lighting the hydrogen on fire. So always keep in mind what is left over in solution, what potential side reactions could occur, and in this case, the side reaction is actually beneficial because this allows us to remove excess magnesium with an acid rinse. Okay, so in effect, you're really wanting to focus on observations and recording your initial and final mass. The initial mass is the mass of copper that you start with through this redox cycle and set of chemical reactions, and the mass of copper recovered is the mass that we end with after all of the drying steps and re-isolation of our solid brick red copper. So at the end of this run through, we're now ready to begin the actual experiment recording. You're going to want to make sure you're recording your data to the proper number of significant figures permitted by your instruments. Today we'll be doing the copper cycle experiment. So first things first, we need to take our 3 clean and dry test tubes. I have a tared beaker all set up, and we're going to record the mass of each of these empty test tubes. So here is test tube 1. Please take your mass reading. Next is test tube number 2. Please take your mass reading of the empty test tube. And here is test tube number 3. Please take your mass reading of the following empty test tube. Now we are to dispense less than 0.02 grams of copper. So what we're going to do, just as my little trick, I'm going to tear this empty test tube in our beaker, and I'm going to transfer copper, and I'm going to make sure my mass is less than 0.02 grams. Okay, so just as a check, right on the dot. So this is the mass of copper for test tube 1. Let's repeat this process for test tubes 2 and 3. So test tube 2 now, don't worry about the mass, I'm just tearing it. I'm going to transfer my copper. I'm going to check the mass now. Here is the mass of our second test tube copper sample. Finally, for test tube number 3, we'll repeat this process. we have too much here in test tube number 3. So let's now transfer a little bit out. We'll reweigh and re-tare test tube number 3. So let's number 3 empty. So here's the empty tared test tube number 3. Let's now transfer our copper. And let's now record the mass of the copper in test tube 3. Let's add a little bit more, so that way we have a substantial reaction. We don't want too much, but we don't want less than 0.01 either. Okay? So here is the mass of copper in test tube number 3. Now what we're going to do is we're going to react our copper sample in test tube 1 with concentrated nitric acid. This is a redox reaction that generates toxic gas. So as a result, we're going to turn on the fume hood. What I want you to observe is after the addition is complete, observe the color of the solution, and then I'm going to add a few drops of deionized water, and I want you to observe the color of the solution once again. I'll be turning on the fume hood at this time. I'll be adding 10 drops of deionized water. So first, please observe the color of the solution before addition of deionized water. And now I will add drops of deionized water. I will then agitate the solution. And I'd like you now to observe the color of the solution after deionized water is added. We're going to pause and repeat this process for our 2 other tests. Our solution in test tube 1 is currently copper nitrate. We're going to precipitate out copper hydroxide via addition of roughly 20 drops of sodium hydroxide. So I'm going to add the sodium hydroxide, 6 molar. So after my first 10 drops, I'm going to agitate the solution with a stirring rod. And then we're going to add an additional 10 drops. We are then going to rinse the contents back into our test tube using a wash bottle. Since we want to make sure we're preserving and all of our transfers are quantitative for copper. Okay, we're going to repeat this process for one more sample because we need a balanced centrifuge before we centrifuge. So let's add our another 10 drops. Let's now agitate our rinsed stirring rod. So note we're cleaning it in between each step. Notice the pretty dramatic color change. Now another 10 drops. Okay, let's continue to stir to complete the reaction. And then let's rinse into our test tube. Okay, perfect. We're now going to load our 2 balanced test tubes into the centrifuge. I'm going to add a little bit of water to the test tube on the left. And the reason for that, the reason why I add a little bit of water to test tube 1 is you want to make sure your centrifuge masses are balanced. I'm now going to load each of my samples on opposite sides of the centrifuge. The reason why they're on opposite sides is so the load's balanced. Now we're going to pause and resume once the centrifugation is complete and I've run test tube 3 through the same procedure. Following sample, we've separated out our solid copper hydroxide from our supernatant liquid. Now to verify that we've completely precipitated out all of our copper hydroxide, we're going to carefully decant and pipette off our top supernatant liquid. We're being very careful not to accidentally pipette over any solid. So notice how it's completely clear, no solid particles. You want to minimize the amount of solid that we have lost in this transfer process. Now it's not going to be perfect, but you want to remove as much of the liquid as possible before evaporation. Now before we remove the remainder of our liquid, what we want to do is we want to test. We want to test to make sure there's no additional copper hydroxide remaining in our supernatant liquid. So we're going to add a few more drops of sodium hydroxide. Okay, next we're going to agitate. And as we have noticed, we do not observe any additional precipitate. So that implies that we've completely precipitated out almost all of our insoluble copper hydroxide. Okay, we're going to repeat this process and decant out all of our liquid for the remaining 2 test tubes, and then we'll come together for the next step where we're generating copper oxide via heating. The generation of copper oxide via decomposition of copper hydroxide. So to do this, we're going to heat our copper hydroxide sample and drive off the water. Now we're going to want to use a gentle flame. So let's first and foremost, let's adjust and prepare a Bunsen burner flame. Let me get the Bunsen burner set up first. So I'm going to have everything closed initially. And then I'm going to open both the gas and the oxygen intake slightly, turn on the gas, and light my flame from the side. So I'm going to reduce the gas. Okay, so I'm going to reduce the gas. And in order to generate a weak flame, I'm going to increase my oxygen intake until I have a pale blue flame with a lightly defined inner blue cone. We do not need a well-defined inner blue cone for this drying step because we want to minimize spatter. Next, I'm going to place my test tube in a test tube holder, and then I'm going to gently bring my test tube into the flame, keeping it pointed away from me for safety. It should be a gentle wafting process, and it doesn't need to be in direct flame for very long. As you notice, it's already starting to dehydrate. You're just going to bring it in now to the flame, keeping it pointed away from you. This is why you keep it pointed away from you, to minimize spattering. And we'll resume once we've dried both of our copper samples. So after heating, I've added some deionized water just to make it a little bit easier to see. Notice the distinct color of the copper oxide solid. Notice how it's distinct in terms of a marquee physical property such as color from our copper hydroxide. And in our next step, we're going to be performing what I would consider a bit of an acid-base reaction, where we're reacting this metal oxide in water with sulfuric acid. Then we're going to proceed with a redox reaction with magnesium metal to regenerate our copper solid. You may want to consult the activity series to prove to yourself as to why magnesium metal can reduce copper 2+ back to copper solid. Okay, so we're going to dissolve our copper oxide in sulfuric acid. So we're going to add sulfuric acid until this copper oxide completely dissolves. So notice how it's bubbling and fizzing during this process, and we're undergoing another color change to generate our good old friend copper sulfate, which is the deep blue solution that you've been handling throughout your laboratory experience. I'd like you now to observe and appreciate the color of our solution after we've dissolved our copper oxide and reacted it with sulfuric acid. We'll repeat this process for our other two test tubes, and then we'll discuss the redox reaction with magnesium. Copper 2+ in our acidic sulfuric acid solution, we're now going to reduce our copper from copper 2+ to copper 0 using magnesium metal. Now this reaction is going to be accompanied by a vigorous generation of hydrogen gas, not from the reaction with copper, but from the reaction with our H+ in solution. That's why we have to add an extreme excess of magnesium. So I'm going to add a magnesium ribbon. I'd like you to observe, and I'd like you to tell me what is the gas being generated in this experiment, and I'd like you to really focus on what's going on at the surface of the magnesium. Is it changing color? So I'm going to bring the magnesium. So here's what a magnesium strip looks like. It's silver metallic. I'm going to drop this into my test tube, and we're going to observe what occurs. And of course, I'm going to keep the test tube pointed away from me, and I'll bring it closer to the camera once the vigorous reaction is somewhat progressed. So as you can see, even from over there, there's vigorous generation of bubbles and heat. Again, you always keep things pointed away from you when you're handling a test tube. Quite an exothermic reaction. That's why I switched to holding it with something other than my bare hands. And I'll bring it close to the camera so you can see, but our magnesium strip has certainly disappeared, and we now observe generation of a new solid. Allow it one moment for the reaction to calm down before I bring it closer to the camera, just so that way we don't have any spill issues. This is a highly exothermic reaction. The test tube is quite warm in this case. Again, always make sure you're practicing proper lab safety and pointing things away from you, and you always have an external device to hold warm objects rather than holding them with your bare hand. I'm going to transfer this to the test tube holder. And now I want you to observe in this reaction mixture, if you notice any additional color changes for our solid, what is coating the surface of our magnesium ribbon, and what would we identify this new solid generated as? And as you see, I'd also like to think, why are we generating so much gas in this process? Okay, so we'll let this reaction continue on, and then we'll resume when we talk about the washing steps. The excess magnesium, we add sulfuric acid dropwise. As you notice, the magnesium is reacting with the acid to generate a gas, and our solution is the brick red color of copper. We'll continue this process, and then we will centrifuge this sample, and we'll return once we have centrifuged our samples, and then we'll talk about the drying procedure. We now have completely reacted all of our magnesium with sulfuric acid. We have our brick red copper at the bottom. We're going to centrifuge this solution and decant, and I have a dummy test tube prepared to ensure that the test tubes are balanced when we centrifuge. We have a little more water. We'll load this into the centrifuge, and then we'll resume once we've centrifuged our copper precipitate to the bottom of our test tube. Now we have centrifuged our copper, so now our copper is sitting at the bottom. We have a perfectly clear supernatant liquid. We're now going to decant and dry our copper. And in this process, the drying is exactly the same as the copper oxide procedure, and we'll return once we have dried our copper completely. Let's now weigh our test tubes. So first, let's weigh test tube 1. Okay, so let's now weigh test tube number 2. We finished drying our samples, so let's weigh our dried copper in test tube number 3.